Okay, so good morning again. I'm going to start presenting the EDO's drought indicators, specifically the soil moisture, SPI, and low flow indicators. And then my colleague Carmelo is going to follow me with the FFR and the CDI. So a good way to introduce EDO's drought indicators could be the consideration on how droughts propagate through the hydrological cycle. So if you consider the hydrological cycle as you see it on this picture, for instance, a meteorological drought could start with a lack of precipitation over a large area and for an extensive period of time. We monitor this phenomenon through the standardized precipitation index SPI. As a consequence, this water deficit propagates through the whole hydrological cycle and gives rise to different types of droughts, such as agricultural or hydrological drought. For example, the low precipitation might cause a soil moisture drought developed, which we monitor using the soil moisture anomalies indicator SMA. Then the decreased soil moisture could affect vegetation and animals. We specifically monitored vegetation using the fraction of absorbed photosynthetically active radiation FFR indicator. Subsequently, slow responding variables will be affected and a hydrological drought can emerge, causing less surface runoff, for example, so which we monitor using the low flow index. And finally, this could also cause a decrease in groundwater. An indicator to monitor this phenomenon is under development right now. By combining SPI, FFR, and SMA into a high-level indicator as the EDO combined drought indicator CDI, it's possible to have a high-level interpretation of the drought impact. And this may also be useful for policymakers and stakeholders who needs, let's say, a synthetic descriptor of drought. And now with this introduction, we can go in a little bit more detail into the indicators. So the standardized precipitation index SPI is used to measure meteorological drought by measuring precipitation anomalies based on a comparison of observed and total precipitation amounts for an accumulation period of interest, with the long-term historic precipitation record for that period. EDO SPI is obtained monthly for the interpolation of observed meteorological point data and graded data from the Global Precipitation Climatology Center, GCPP. And it's calculated using the reference period of 30 years. Now, since SPI is calculated over different precipitation accumulation periods that typically range from 1 to 48 months, the resultant the different SPI indicators allow estimating different potential impacts of meteorological drought. So, for example, when an SPI is computed for shorter accumulation periods, let's say like between 1 and 3 months, it can be used as an indicator of immediate impacts, such as reduced soil moisture. When it's computed for a medium accumulation period of 12 months, it can be used as an indicator for reduced stream flow and reservoir storage. Or when it's computed for longer accumulation periods like 88 months, it can be used as an indicator for reduced reservoir and groundwater recharge. So the SPI calculation process can be summarized in the following way. So first, the precipitation data is aggregated on a particular period of interest. Then the gamma distribution parameters are fitted using the frequency distribution of the historical rainfall accumulation of all years of the available time series. For any observed rainfall accumulation, the cumulative probability is then derived. And finally, the cumulative probability of the observed rainfall is then transformed into the standard random variable set. This transformed value is what we call then the SPI. So increasingly severe precipitation deficits are indicated as SPI decreases below -1, while increasingly severe excess precipitation is indicated as SPI increases above 1. So before entering into the details about EDO, soil moisture anomalies, and low flow indicator, I think it's important to point out that they are calculated using outputs of the least flood hydrological model. So least flood is a hydrological rainfall runoff model which has been developed in-house here at the GRC in order to reproduce the hydrology of large transactional European river catchments, and which currently runs operationally within the Copernicus European Flood Awareness System, known as EFAS. So the input data of least flow model includes daily meteorological observations from the European continent, updated with a 2-day delay, which are obtained from the GRC Mars agri-forecast database, and which are extended for 7 days using numerical weather forecasts produced by the European Center of Medium Range Weather Forecast, known as the ECMWF. Least flood has been updated recently, and its new version covers a bigger spatial domain. As an example, here we have a soil moisture anomalies indicator map for the current and for the previous version. Clearly you can see here that the current version added more reservoir of countries on the East Europe and Turkey and Cyprus, as well as some of the river basins discharging in the Mediterranean in North Africa. As I said before, the SMA indicator implemented in EDO is computed based on estimates of daily soil water content, which is one of the outputs parameters of the least flood model. The SMA indicator is used for determining the start and the duration of agricultural drought conditions, which rise when soil moisture availability to plants drops, let's say, to such a level that is adversely affecting crop yield. EDO SMA is aggregated to 10 days and presented as anomalies or a statistical deviation from the long-term mean, and is calculated with the baseline period of 1995 onto the last available full year. The SMA indicator in EDO is computed every 10 days as anomalies of soil moisture index SMI. So for the calculation of SMI, the soil water content theta is converted into SMI by normalizing the soil moisture between the wilting point and the field capacity, following the approach suggested by Van Jennuten in 1988. The SMI is equal to 0 when the soil is severely dry, and let's say when it reaches the wilting point, and equal to 1 when the soil moisture is above the field capacity. This is giving a measure of the degree of water stress suffered by the vegetation. In order to understand the variations of SMI values in the past climatology, we calculate the 10-day SMA as a statistical deviation from the long-term mean. This statistical variation expressed as units of standard deviation is divided, as you can see, into 7 classes. That goes from -2, so values that indicate conditions wetter than normal, and 2 is a value that indicate conditions drier than normal. So the low flow index is another indicator using the least flood outputs. This indicator was developed within our group, and it exploits the least flood simulated daily river water recharge to capture unbroken consecutive periods of unusually low stream flow, and then it compares the water deficit to the historical climatology. So in order to calculate the low flow index, a threshold value of flow rate Q is computed for each calendar day for a 22-year baseline period. This threshold represents a river natural flow regime and accounts for possible seasonality in the stream flow values. So it is represented by the black line you see in the upper left figure. The threshold values are computed based on the flow duration curve, which plots a river flow rate Q against the percentage of exceedance. and are defined as the stream flow values corresponding to the 1950 percentile of the flow duration rate. Let's say, in other words, those flow rates that are equal or exceeded for the 95% of the time. So based on that threshold, hydrological drought is defined as a period of consecutive days with discharge lower than the threshold. So the ones that you see in red on the figure. Then the total deficit of a particular event is calculated by adding all those deficits. So the cumulative distribution function of the total water deficit F represents the probability of observing values less or equal to the total deficit of an event. And this quantity is used as a direct standardized measure of the, let's say, severity of a given deficit, and constitutes what we call the low flow index. The low flow index is dimensionless, ranging from 0 to 1 in terms of real values, and from yellow to red on the map, as you can see, where 1 corresponds to a maximum drought severity. And on the left, we have an example of EDO's low flow index map for the 10 period day of February of this year. As you can see, the EDO low flow index is displayed over a matched river network from the list flow 5 by 5 kilometer network and high detail 100 by 100 meters river catchment database network. The EDO low flow index has been shown to capture effectively the starting rate, the duration, and the spatial evolution of the major historical hydrological drought events in Europe. As you can see, also 4 classes are considered, varying from low hazard to very high hazard, when the index is above 0.75. So now I'm going to leave you with my colleague. He's going to continue.
So I'm going to wrap it up, this first part of the presentation, by after following the propagation of drought through the hydrological cycles, as shown by Carolina, we are going to show you some of the key indicators that we're using for monitoring the agricultural or vegetation drought. First of all, I want to answer the question why we have this focus on agricultural drought. And the answer is that agricultural drought is often considered, it's one of the easiest to understand amongst the drought, and people, when consider a drought event, they immediately recognize the connection between agricultural productivity and drought. And also, drought can affect agriculture directly by the lack of rainfall events, but also indirectly by competition between different sectors, for instance, the irrigation sector with other water supply sectors, so through the water scarcity issue. In general, agriculture or plants and vegetation in general can respond to a drought event with different signs, like showing vegetation water stress, an increase in the temperature of the leaf of the canopy foliage, a stomatal closure, which reduces the CO2 productivity, a reduced photosynthetic activity, reduced growth rate. But all this effect on vegetation have in common the fact that this reduces the greenness of the vegetation. So so this is the reason why in a monitoring drought system we consider interesting and visible to have a vegetation greenness indicator to monitor the evolution, the effect of drought on vegetation. Specifically in our system, we decided to use the fraction of absorbed photosynthetic active radiation, or FAPR, as indicator of greenness. The reason why we choose this indicator among the larger array of indices available in the scientific literature is because it's a physically based quantity that it's included by the United Nations amongst the 15 essential climate variables. It's directly related to primary productivity, so even if it is not a quantification of primary productivity, it's directly related to this quantity, and also can be easily retrieved from remote sensing data, so give us the opportunity to have a global coverage with a good spatial resolution without much effort. Specifically for EDO and GDO, what we are using, it's the satellite product derived from the MODIS satellite. The reason why we use MODIS data, it's because it provides a long, temporally consistent time series of data starting in 2001. So right now we have 18 years of continuous data collected from the same sensor, which is uncommon for remote sensing data, I would say. Also, it's available on near real time with just 1 day of delay, so allow us to have to decide the right updating of time scale of the system. It also has a moderate to high spatial resolution up to 500 meters, so give us also good spatial details for a continental or global scale system. In details, what we do, so we are not using the FFR as direct measure of the drought, but we use the standardized score analogously of what we do with the SPI and the soil moisture anomalies. So we basically quantify the deviation of the current FFR from a long-term climatology of the FFR. So we basically quantify if the current conditions are more green or less green than the usual condition based on historical data. And then what we usually show is not actually the FFR anomalies itself, but it's a classification of this data in 7 classes, which is updated every 10 days, as we do for the soil moisture. And there's a spatial resolution of 0.01 degree, which is approximately 1 kilometer. Of course, the problem of using a greenness indicator in drought analysis is the fact that not all the reduction in greenness are related to drought. There can be other factors that contribute to reduction in greenness. A real simple case can be a fire forest events, which reduce clearly the greenness of vegetation, but is not related to a drought or not necessarily related to a drought. So in order to use effectively this FFR information in a drought monitoring system, we developed what was already introduced by my colleagues as the combined drought indicator. So this indicator doesn't use only the vegetation indices as measured for the drought, for the agricultural drought, but it also uses a conceptual scheme of cause-effect approach to see how the hydrological components of the drought can drive to an actual agricultural drought. So how the system works. Basically, we start by watching a precipitation shortage, usually focusing on SPI 1 and 3, because as Carolina already said, these short times SPI usually are more related to agricultural impact on agriculture. So these anomalies on precipitation can raise a watch alarm, so a situation that should be followed carefully because it can drive a following effect on vegetation. Then, when this precipitation shortage overlaps with a soil moisture also deficit, then we release a warning status, which means that even if we cannot see yet a direct effect on the vegetation, we already see that there are signs that something can happen on the vegetation. And then as soon as we have also an anomalous condition on FFR, then we release the alert, means that the vegetation is already impacted by the drought. And then we have some other classes related to the recovery, so that follow the end of the drought and how the plants recover to the normal condition. So in this way, we can have, using precipitation and soil moisture anomaly, we can have an early warning information on possible effect on vegetation, even when the vegetation is still in normal condition. Also, we can remove all the events that show anomalies in the vegetation but are not related to actual drought or precipitation or soil moisture deficit. And also this index, combining all the information that are provided by precipitation, soil moisture and vegetation, give us a synthetic descriptor of the agricultural drought. So in a single maps, a policymaker, a decision maker, or stakeholders can just look at these maps and understand in a simple way in which phase of the drought processes we are at the moment in the event. So with this slide, we are going to close this first part of the presentation. Now we will have a break for question and answer, and then we will come back again with me and going with an hands-on demo on the OiEau. We were looking at the system, directly on the system, and we'll look at all these index in action on a real study case.